Hello. The topic of today's lesson is line graphs. We're going to read line graphs, we're going to make our own line graphs, and we're going to interpret and analyze them. My friends, we're still in the data science unit where we're learning how to represent data. And different representations or visualizations work for different purposes. We've looked at bar graphs, we've looked at line plots, we've looked at picture graphs in earlier grades, and today we're going to introduce line graphs. Line graphs are fantastic visualization tools to see how rapidly your data points are increasing or decreasing or they're remaining flat relative to each other. So let's take a look at the first problem. The length L of a rectangle is 2 centimeters more than the width. My friends, it is very simple to translate this problem into math, this English into math, by saying L for length is W plus 2, or length is equal to width plus 2 more. So we know that length is longer and width is shorter, and the difference between the two is 2. So we can come up with this little table of values. I'm going to label it, fat pencil. Table of values. And you read it this way. If width is 1, length is 3. And we can write it as an ordered pair. Ordered values pair, right? If length is 2, the length is width is 2, the length is 4. If length is 3 plus 2, the width is 2, the length will be 5, and so on. And we came up with 1, 2, 3, 4 points and 4 ordered pairs. What we can do, we can plot the width and length in such a way using the line graph so we can visualize the relationship between the width and the length in the rectangle. For example, first point is if width is 1, length is 3, and the last point is if width is 4, length will be 6, right? Every time it increases by 2, increases by 2. So right here with this line graph, or simply linear graph, we see the relationship between width and length. We see the relationship between width and length. And we can kind of predict that this relationship will continue to be this way for many values of width, right? There can be many multiple points, values, inputs for width and outputs for length. So when the points are connected, we get a straight line. It's called linear relationship. We add 2 every time, right? There's no division, multiplication, plus 2, plus 2, plus 2. For each value of width, we can say the length will always be plus 2. It's a linear relationship between width and length. And we use the coordinate plane to visualize this relationship. How can we use the grid, or we can say the graph, right? We can say the graph, same thing, to find the length of the rectangle if the width is 6. Well, here is how we would do it. We would first identify, start from 0 and go all the way until 6. So I do see, here is my 6, right? Here is width equals to 6. Then I would go all the way up to my graph until I hit the graph right here. And I would plot a new point. Let's make it in red, just like it was before. So this is the new width when it's 6. What is the length? Well, we would go all the way to the y-axis, to the vertical axis, and we would hit 8. So we know if the width is 6, the length would be 8. Okay? So we can say if width equals to 6 centimeters, then, right? You see this if, then length would be equal to 8 centimeters. How do we know it? Of course, we could have said 6 plus 2, but that's not the point. The point is to use our graphical representation of this relationship. And we can predict the values of width and length all the way into large numbers. This is a very simple relationship, just plus 2. But in the real world, we can build very complicated models and visualize them and predict how relationships will behave with each other using those graphical lines. Let's practice a little bit more. On the following page, we have a different example. We have a different example where the first 4 terms of a sequence, we have ourselves a sequence, and maybe this is the first time you hear that word, but sequence is really just a list of numbers. It's a list of numbers in a specific order. Sequence, again, is a list of numbers in a specific order. And these sequence A, right? So let's label it. This is our sequence A. And we are given 4 terms of a sequence. We have 1, 3, 5, 7. Each term is obtained by adding 2, right? By adding 2. So look at this. Plus 2 to the previous term. 5 plus 2 generates the next term, and so on, plus 2. And of course, we can say 1, 3, 5, 7, 9, 11, 13, and 15 are the next terms in a sequence. These are the terms, okay? These are the terms, the members. The list of the sequence is made up of terms. Now, let's come up. First term is 1, 1. The second term is 2, 3, 3, 5, 4, 7 in parentheses. 5, 9, right? Fifth term is 9. Sixth term is 11. Seventh term is 13. And finally, eighth term is 15. We only need 8 terms. Okay, very good. So that's our sequence A. Now, on the opposite, we have a sequence B, right? Sequence B, I need to use a different marker. Sequence B also starts with a 1, but it is generated by adding 4 to the previous term. So let's generate more numbers in a sequence. So we have 1, 5, 9, right? Every time, plus 4, and so on, plus 4. So 9 plus 4, let's go. 13 plus 4 more, 17, plus 4 more, 21, plus 4 more, 20. 5 plus 4 more, 29. Let's generate the pairs, the ordered pairs, x and y. 1, 1, 2, 5, 3, 9. Fourth term is 13. Fifth term is 17. Sixth term is 21. Seventh term is 25. And finally, last term, eighth term, is 29. So we've generated the sequence. Now, copy and complete the graph below, extending the y-axis. Plot both sequences A and B on the same graph and connect the points. So what they've done, they started us on this little graph paper that is just 10 by 10, right? So this is your x, this is your vertical y, and it only goes up to 10. But they're asking us copy and complete, extending all the way to the 8th term. So I already created a graphing paper. I created graphing paper right here. I inserted the new page. And let's continue. Let's plot the sequence. What color did I have for the sequence A? I had blue. So let's continue using blue so we're consistent. So we had a point 1, 1. Then we had a point 2, 3, right, for the sequence A. Then we had a point 3, 5. I keep just copying from the table of values. Then we had then we had 4, 7 right here, and then we had 5, 9, right? And then the 6th term was 6, 11, right? And then we had the 7th term was equal to 13, and the 8th term was equal to 15 right here. Now I'm going to make a straight line, connecting all these points right here. Okay, that's a straight line. And I can even say it's going to go on like this forever. Now notice, my friends, that I have this interesting dependency. Up 2 over 1, up 2 over 1, up 2 over 1. Each time plus 2 plus 1 plus 2 on the y and next term. So each time I'm generating a new point, it follows the same rule. And of course, when I connect these points in sequence, this is my sequence A, right? Let's label it. Let's label it. This is my sequence A. Okay, when I generate new points, they all follow the same rule because it's part of the same pattern. Now let us pick up an orange color and let's plot or graph the line for sequence B. And we also, sequence B starts, let's pick up orange color, also starts at the same point, 1, 1. But then it goes on a little bit different. The second term is not, it's already 5, right? It's like much steeper line. Look at this. The third term is all the way up to 9. The fourth term is 13, right? So 9, 10, 11, 12, 13, right? That's the fourth term. And the fifth term is, again, we're going up. 1, 2, 3, 4. Remember, we were adding 4 and over 1, right? Right here. And the fifth term, the sixth term, 6 terms is 21. So again, 1, 2, 3, 4 and over 1. So right here, okay? So I'm going to pick up my pencil and I'm going to connect all these dots, and I'm really hoping to make a beautiful straight line right here, right here. And again, this line goes on forever. So I'm going to put an arrow. And notice every time I add 4, it's plus 4, right? Plus 4 to generate the next point. Why? Because the sequence was add 4 to the next one. Add 4, add 4, add 4. Now let me label it. This is sequence B. Now that we've plotted them, let's answer some questions. What type of line can be used to connect the points for each set of data, right? Right here. What type of line? Of course, it's a straight line because we talked about it. It's a linear relationship, right? Straight line. It follows the same pattern, plus 2, plus 2, plus 2, plus 4, plus 4, plus 4. Now, find the distance between each set of points for each term. Find the distance between each point for each term. Well, copy and complete. Notice this. The distance between the points in sequence A and sequence B right here. So for the first point, there is no difference, correct? For the second point, notice the difference is, let me pick up a different color right here. The difference is plus 2. Between third and fourth point right here, right? The difference is 4. And this difference keeps growing. This difference, so this is 2. The next one is 4. The next one is 1, 2, 3, 4, 5, 6. This difference is 6, right? So 6. And of course, we can continue because right here, right here, I'm going to make a straight line between the same points, right? This is our point number 5. This is the fifth term. And look, the difference is 8. And of course, we don't have to count because it follows the pattern 0, 2, 4, 6, 8, 10, 12, 14. We don't even need to look at the graph. We see it follows the same pattern. What can you conclude about the distance between each corresponding point in the two sequences as the term increases? The distance is becoming wider and wider, right? The points of the same term are becoming, look, there's no difference between the first term, right? They're both start at 1. Then they separate by 2. Then they separate by 4, by 6, by 8, by 10. They're becoming wider and wider because sequence C is, the distance is increasing, right? The distance is increasing, and because the lines are separating, the orange line, the sequence B, is much steeper. It's much more rapid increase, okay? Rapid increase. That's why the lines are separating. Now, let's take a look at example 2. These are very common arithmetic patterns. A restaurant has triangular tables. Each table can seat 3 people, right? 1, 2, 3. As you put for larger parties, tables together, of course, you have to push more chairs around. So for 1 table, we have 3. For 2 tables, we have 4. For 3, we have 5. Notice 3, 4, 5, 6, 7, 8, and 9. Let's create ordered pairs here. When we have 4 tables, right? 1, 2, 3, 4, we will have 6 chairs. When we have 5 tables, we will have 7 chairs. When we have 6 tables, we have 8 chairs. When we have 7 tables, we have 9 chairs. Another restaurant uses square tables, and each of which can seat 4 people, right? We know 4 has 4 sides, so this square has 4 sides. So let's generate the number of chairs. We have how many seats? 4, 6, 8. What do you think will be next? For 3 tables, we have 1, 2, 3, 4, 5. Oh, for 4, right? For 4 tables, we will have 10 chairs, 12 chairs, 14 chairs, and 16 chairs. Let's come up with ordered pairs. 4 tables, 10 chairs, 5 tables, 12 chairs, 6 tables together, 14 chairs, 7 tables, 16 chairs. Let's put them in parentheses, just like the notion. Now, my friends, what we can do, we can come up with our own line plot, right? Let's copy. It says copy and complete the graph below. Extending the y-axis. My friends, I don't have to come up with another graphing paper. Let's just say for my triangular tables, right? Triangular tables are, is this red? 1 and 3. No, these are my triangular tables, right? These are my triangular tables. Okay, and for green, do I have a green marker? No, I don't have a green marker. That's a shame. And for green, I will have square tables. Square tables. My friends, take a look. I can just simply extend the line. It's a straight line that follows the same pattern. The same pattern. And it can go on forever for whatever number of chairs. So for 10 chairs, let me make a fat triangle. The triangular table will have 12. For 10 tables, for 10 triangular tables, we will have 12 chairs, okay? For 10 tables, we will have 12 chairs according to our graph. And the same thing would happen if we extend the square tables. Plus 2, plus 2, plus 2, like this. And the way I always look at it is like 1, 2 for the next term, 1, 2 up for the next term, plus 2 up next term, plus 2 up next term. So all of these are additional points on my line. It looks a little bit messy, but I hope you get an idea how I generate the longer line. Let's answer the questions. What type of line can be used to connect? Of course, straight lines, right? We have a linear relationship, straight lines, right? For both triangular tables and square tables. How far apart are the points for each line when the number of tables is 3? So here is 3, right? Let's use this marker. Here is 3. Let's see, right? So for 3 chairs, this is our tables, right? I can label this. These are the tables, and these are the number of chairs, right? These are the number of tables. So for 3 tables, we will have 3, 5 versus 3, 8. So it's always plus 3, right? They're 3 apart. Now, let's take a look. Watch. For 4 tables, we will have 4 apart. And for 5 tables, 1, 2, 3, 4, 5, we will have 5 apart. So what if the number of tables is 15? It will be 15 units apart. 15 units apart. So I hope you find this useful. I hope you see how the simple sequences that have plus 2, plus 4, plus 1, plus 3 end up being represented as straight lines. But some lines are steeper and some lines are not so steep, depending how fast your pattern is growing, right? Some slope up very fast and some are very mellow.